versus southbound? And the answer to many of those is yes. And so what you're about to see, and this is the first time in today's class that you will see quantities are not just important for their number. And so speed is a number, a value, but just as important as direction. You see, if they got in their car and they did not travel at 60 miles per hour, if they were traveling at, say, 10 miles an hour, they would not get to LA in 2 hours. It doesn't matter what direction they go. So their speed is important. I get that. And most people get the speed is an important part of that. But I want to emphasize direction is just as important. Now, this is not a face-to-face class, but I often ask students when they're in here face-to-face, I said, okay, class is done in a little bit, and you leave and you go to get to your car. Does it matter if you go west versus east? It does. And so direction is really important. As you'll see as we continue, if I have a big object in front of me, do I get the same results if I push it to the north versus pushing it to the west? See, I don't. The direction I push it is important. And so there's a lot of physical quantities that need a number and a direction. And so that's that subtlety between speed and velocity. Velocity technically is the number, the speed, and also the direction. So if somebody asks you for the velocity, you're not completely answering it unless you say the number and the direction. So the velocity of a car would be 60 miles per hour to the north. Or the velocity of my bike is 7 meters per second to the east. And I have to include a direction. So the speed is just the 7 meters per second. And that's what I meant by earlier on, that if I just take distance and divide it by time, all I get is a number. And I just get the speed part of it. I just get the calculation. And so for a lot of calculations, that's what we're after. We're after the number. But to really understand the whole story, we want a number and a direction. And these are called vectors. Something that has a number as well as a direction. So when you push on something, what we're going to call a force, we're going to say it's a vector because it's important to know how much did you push on it, and also, just as important, what direction did you push. And so in the next couple of chapters, and particularly the lab tomorrow, we're going to emphasize this. We're going to say that direction is just as important as the numbers. And we'll do a little experiment to show ourselves that it's not just the numbers, but it's also the direction. And so we'll push on things and worry about the direction. All right, so keep that in mind. So that's this little difference. Well, I better keep going. Let's see, how long have I been talking here? I should have looked. Is there time on there?
Right there.
41. Okay. So actually that's good time. So we're about 41 minutes into this, and that's about perfect. Because I'm going to put a line here and just emphasize this is the first half of the chapter. What is speed, and how is it different from velocity? And what do we mean by average versus instantaneous? So let's take one more step. That's why I wanted to leave this chart up here, because there's another question that would lead off of this one. For example, let me just put my marker down here. Let me stand on this side of the room, and as I was showing you, if I were to move across the room, okay, so 10 meters, and it took me 5 seconds. If I took the whole distance and I divided it by the whole time, that would give me my average speed. Because watch this for a moment. What if the motion was a bit more complicated? What if I started over here and said, okay, I'm going to go to that side of the room, and I'm real excited about going over there, and so I start off and I go faster, 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 and I get about halfway through the room, and I get tired, and I go slower, 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 and then I finally make it to the other side of the room. You see, the instantaneous speed has varied. That is, way back here, I would be starting with 0 speed, and I would begin to go faster, faster, and faster. But if it took me a whole 5 seconds to get across here, at the beginning, those first 2 meters, it probably took me more than 1 second to get there. In other words, my speed is kind of slow over here. Kind of in the middle of the room, I've picked up my speed. Now I'm just jamming. You know, maybe I'll go 2 meters in less than a second. And so I'm going at a speed greater than 2 meters per second. And then on this side of the room, I start to get tired, and I begin to slow down, and I now go less than 2 meters in 1 second. And so if I just took the whole distance, 10 meters, and divided it by the whole time of 5 seconds, that would give me my average. But that's just like my story about going to Dodger Stadium here. That doesn't tell me everything about this motion as much as I would like to know. I would like to know, what is my instantaneous rate? What am I doing now? Like here, I may be going only 1 meter per second. Where in the middle of the room here, I'm going 3 meters per second. And back at the beginning, where I was trying to pick up speed, I'm only going 1 meter per second. And so my instantaneous speed is changing as I go along. And so for me just to say my average speed is 2 meters per second, although that's true, it doesn't tell me enough information. It doesn't tell me that, hey, I was going less than 2 meters per second at the beginning, and then more in the middle, and then less again near the end. So, how could we fix that? How could we describe it better? What is our next question? And this is the second half of this chapter. Let me come over here. And so I might make, and it's kind of the same question, it is a rate question. I might ask, how is my instantaneous velocity changing? And so I might say, let's look at the change in the velocity. And of course, see how much time is taken for that change. And so I would call this then a rate. Now, it's not a rate of how my distance is changing. That's what speed is. So I don't want you to confuse these two rates. This is the rate at which my speed is changing. So again, if I just kind of use this as an example, if I start back here at a speed of 0, and I go faster and faster and faster until about halfway, and so I'm about 2.5 seconds into my motion, because remember, it's going to take me 5 seconds to go all the way across. Right? So from here, 0, to here, let's just call that 2.5 seconds. I would go from 0 speed up to, let's just say 3. Because this is the part where I'm going really fast. This is the part that I'm going more than 2. And so this is how my speed is changing. And so I'm kind of curious about that. That's my next question. And that's my new quantity. And so these are the two big quantities. And some of you, I think, are already guessing. If this was a face-to-face class, I would say, what do we call this? And this one's not as common as all the other ones we've done, like speed and velocity and volume and area. So you may not know this one, but usually one or two people in the room know this word, and we call this then the acceleration. And this chart right here really summarizes Chapter 2. Chapter 2 is trying to introduce you to what is speed/velocity and what is acceleration. And how are these different? How is speed different from velocity, and how is acceleration different from velocity? And let's give it a symbol. And as I mentioned yesterday, I was saving the lowercase a for acceleration. So that's why we use the capital A for area. And likewise, I don't know if I said anything earlier on, but we did the capital V for volume yesterday so that we could have the V for velocity today, the lowercase v. All right, well, I hope this discussion and the next 4 steps made sense to you, because we're going to keep doing this over and over again. We're just going to ask a new question, this new quantity. And we're going to try to understand this new quantity. And for us then, this new quantity is called acceleration. And so here is our definition. Here is our concept. We are asking, at what rate is your instantaneous velocity changing? And let's go through those 4 steps again. The 4 steps are, first step, think about a new question. Think about a new idea. And so this is acceleration. And this is the most advanced one we've done so far. Acceleration. Okay. But if I put that little formula up here, and so let me just use the symbol A. Let's see if we can make a formula, step 2. And the formula is usually, it's something this simple, kind of give it away, right? It's saying, what's your change in velocity? And so our symbols are the Greek letter delta for change, and then V for velocity, so that would go in the numerator. And in the denominator, we would put the time it took. I'll just label it as a delta t. How much time did it take? All right, so that's step 2. What's the formula? Step 3 then would be, okay, so what are the units for this? Well, maybe it'll help to do this calculation. Okay, so again, let's just pretend I'm over here on this side of the room with 0 speed, and 2.5 seconds later, I now have a speed of 3 meters per second. So what I would put here is, this would be my final speed minus my initial. And then this would be the time it took. So in this little case, my final speed would be 3 meters per second. My initial speed would be 0 meters per second. And the time it takes is my 2.5 seconds. Now let's run through the math, and again, let's watch our units. I'll do the numerator first, because we should subtract these two, and so 3 meters per second minus 0 meters per second. Well, let me just kind of put over here, if I had 3x minus 2x, you've probably done this so much you would just say, oh, that's 1x. Sure, but you do it this way. You say that they each have a common factor of x, and you factor it out. Then you have a 3 minus a 2, and you get 1x, which we don't usually write the 1, so we just write x. And I could say the same thing here. A 3 meters per second minus 0 meters per second. The meters per second, if I treated it like this x, would factor out. And I would then just have 3 minus 0, which would leave me with 3 meters per second. So notice, it's still the same units, meters per second. It wasn't squared or cubed or anything. But I just want to emphasize, notice I follow the same rules of mathematics for my units that I do for my numbers. And then in the bottom, I have my 2.5 per second. Well, maybe I'll grab a calculator for the numbers on this one. But if I just do the numbers, 3 divided by 2.5 is 1.2. And I don't think you'll have troubles with the numbers. But let's look at the units again here. This goes back to our compound fraction. Maybe we should write it as meters per second divided by a second. Now, if we then write this, maybe I'll do it down here, 1.2 meters per second, and make this a compound fraction. And like we mentioned earlier, compound fractions you flip and multiply. So 1.2, and I'll put meters per second. And then this flips, and I get 1 over second. And maybe I'll carry it up to here. So this would be 1.2. And then this would be meters per. And this one's kind of interesting. And like I said, this is more advanced than anything we've done so far. And some of you may not even have ever seen this before. Second times a second is second squared. And so this is our step 3. What are the units to measure this new quantity called acceleration? And so let me put that in the table here. This would say then, meters per second squared is the appropriate units to measure acceleration. So step 1, new question, new quantity. Step 2, what's the equation? Step 3, what are the units to measure this? And step 4, as I said yesterday, maybe the most important. What does it really mean? When you say that my acceleration is 1.2 meters per second squared, what does that even mean? I think the better answer is, before we simplify this math, back here, even though it's not in the most simplest math form, it probably is in the more simple or conceptual form. Because let's read it this way. 1.2 meters per second each second. You see, what this is saying is my velocity is changing. That's what acceleration measures. Acceleration measures how my velocity changes. It doesn't measure how my distance changes. That's what speed measures. That's why acceleration and speed are different and so easy to mix up. But here, the acceleration is measuring how my speed changes. And so this is saying that my speed is changing by 1.2 meters per second each second. Watch, see if this helps. All right, I'm on this side of the room. I'm starting with the 0 speed, and I'm going to go faster and faster and faster and faster. And by the middle of the room, after 2.5 seconds, I should be going 3 meters per second. So what's my acceleration? Well, as we just did in the math, my acceleration is 1.2 meters per second each second. To try to understand that conceptually, I would say this, that if I start on this side of the room, and then I start running, after 1 second, my speed would increase to 1.2 meters per second. So from 0 to 1 second, I would increase 1.2. So now I would be going 1.2. But look at the next second. The next second, I would go up. I would increase my speed by another 1.2 meters per second each second. So after 2 seconds, I would be going a speed of 2.4. Did you get that, where I got the 2.4? Right? The 2.4 is saying that every second you are to increase your speed by 1.2. So from 0 seconds to 1 second, I would increase to 1.2. From then 1 second up to 2 seconds, I would increase another 1.2. And so 1.2 together with 1.2 is 2.4. So my speed after 2 seconds is 1.4. I'm just sorry, 2.4 meters per second. And so that is what this means. Now, if I go for another half a second, right, because remember, I got to this speed after 2.5 seconds. If I'm going to increase my speed another half a second, that means I wouldn't go a full 1.2 meters per second increase. I would go half of that much. And half of that much is 0.6. So after 2 seconds, if I'm already going 2.4, in another half a second, I would add 0.6, and I'm going 3. And so that's what acceleration is. And you can see I spent a little more time here on acceleration. I think for 2 reasons. Number one, or 3 reasons really. Number one, it's not as common. Number 2, I think it is just harder to get acceleration and get students to understand acceleration. And 3, the units are just totally different. These are more complex units. And in fact, I have a suspicion that those of you who have done acceleration have probably seen meters per second squared. I would just ask, have you seen it written this way? Meters per second each second. Because I think everybody should. This gives you the understanding of what the acceleration is. So again, I hope I hit those 4 things. Number 1, new idea, acceleration. Number 2, new formula and the meaning behind that formula. Okay, good. Number 3, what are the units used to measure acceleration? Meters per second squared. And what are the meaning of all of this? And in this case, I think to understand the meaning, it's better to come back a couple steps and to think of it as meters per second each second. In fact, you'll see as we go forward, I'll oftentimes use meters per second each second in my verbal description. Although when I put it on the board and do a calculation, I like it in its simplest form. That's why, you simplify the compound fraction. It makes the math a little bit easier. So when you write it mathematically, it's really nice to write it this way, meters per second squared. But when you say it to somebody, when you describe it to somebody, it's nice to say, oh, my acceleration is 1.2 meters per second each second. So they clearly hear that, hey, I'm gaining a speed of 1.2 meters per second every second. Well, as I said, that's really the whole chapter. But the rest of the chapter and the rest of the time, let me see, by showing you some experiments, if you're kind of getting that distinction between position, velocity, and speed. All right? And so I brought out a little experiment. Let me give myself some room here and make myself a little chart. But to see if you kind of understand that difference, and it takes a little while to distinguish between those two. Let me just make a chart, and the first thing in this chart, I will put time, and I'll measure it in seconds. And by the way, here's a nice and common and convenient way of making a scientific table. You put the symbol of the quantity, and below that you put the units. That way you just have to put numbers in your chart, and you never have to keep writing the units. Okay? And so here's the experiment I'm going to do. Move the camera over to here. I'm going to take this ball, I'm going to put it right here on this edge, I'm going to let it go. And as it goes, it's going to roll down this incline. And if we count it out time-wise, and so right when I let it go, 1 1,000, 2 1,000, 3 1,000, 4 1,000, we have built this so that it'll be on this ramp for 4 seconds. It takes a full 4 seconds to go across. Right, so I'll do it again. 1 1,000, 2 1,000, 3 1,000, 4 1,000. Okay? And so if I come back over to my chart then, I might say, okay, what's going on with this object at 0 seconds? After 1 full second. After 2 full seconds. After 3 full seconds. And then finally when it gets to the end of the ramp, after 4 full seconds. And what I mean by what is it doing, how do I describe it? I would say, okay, given this time, what is the acceleration of it? What is the instantaneous velocity of it? What is the total distance it has traveled from when I let it go? And so these are those 4 quantities I was talking about. And what this chapter is all about, this describes our motion. What is its time? What is its distance? What is its velocity? What is its acceleration? And those 4 parameters are all tied together. All right. Well, to answer this, I got to give you a little bit of information. And that information is going to be this. We'll see it better when we get into the next chapter where we say, let's explain the motion. But the acceleration is actually determined by the slope of this hill. That is, if I were to hold it up higher like this, it would go down and have a different acceleration than in here. Or if I took one of these boards out and it's a little lower, it would even have a lower acceleration. So it's gravity, or at least partly gravity on this incline that pulls it down. So this right here has the same slope. And so for us to start this problem, I need to just tell you right from the get-go here that I've built this. Not only its length is long enough that it'll be on here for 4 seconds, but the slope is built so that the acceleration is 30 centimeters per second each second. By the way, did you see how I said centimeters per second each second, but I wrote it as centimeters per second squared. All right, so there is one little subtlety here. I did change from meters per second squared to one of the prefixes. This incline is so shallow that the acceleration is not that big that it just makes more sense to do things in centimeters. All right. So that means that in my chart here, I should put units of centimeters per second squared. And so I'm going to be asking you to tell me what the instantaneous speed is at each location. And I'm going to be asking you how much distance did it travel. And as you will quickly see, you will have homework problems exactly like this. And you can either make a chart or do a calculation. Hopefully I'll do both here and you'll see that. Okay? Now, the first part of this is interesting because I'll come over to here right at this edge And right when I let it go, so I'm going to come over here and let it go. Right now, I let it go. Let me go back. Right here. At time equals to 0. Right there. Right now, I let it go. Can we fill in this chart? I'll start with probably the easiest one in this chart. How much distance has it moved at this point? Right when I let it go. Well, again, if it's face-to-face, I'd wait for a moment, but most people say, well, 0, it hasn't moved anything. Yeah, absolutely right. All right, so the distance that has moved so far is 0, but obviously a second later, it's not 0 anymore and getting bigger and bigger and bigger and bigger. Okay, but what is its speed right there? Well, again, I usually pause and face-to-face. People go, well, isn't that 0 also? Yeah, okay, it's 0. But does it stay there? Well, no. I mean, it starts at 0, right, when you first let it go. Right, when I first let it go, it's 0. I get that. But then it continues on, and it starts to get bigger and bigger. Okay. Because now we finally get to a hard one. What's the acceleration right when I let it go? Now, if this was face-to-face, usually I hear a bunch of answers. And one of the wrong ones is 0. Because what would 0 acceleration mean? This is a good point. And really the main point of this chapter. Are you getting the difference between these two? Acceleration is not speed. Acceleration is how it's changing in speed. So you could have like an airplane going 600 miles an hour. And as this airplane's going 600 miles an hour, I would say it has a huge speed. But if that airplane kept going at 600 miles an hour, I would say its acceleration is 0. It's not changing in speed. So just because this one's big doesn't mean this one is. Or the other way around. This one doesn't mean the same as that one. They're the rate at which they are changing. And how they're changing isn't necessarily the same as what they have. For example, all of you out there, students, each of you may be snacking while you're doing your video here, and maybe you bought a candy bar and it cost you $1. So you all changed by $1. You all are poorer by $1. You spent $1. But that doesn't mean you all have the same amount of money. Some of you had $100 before you spent that $1. And some of you only had $1 before you spent that $1. And so how much money you actually have is totally different and totally independent on how much that candy bar cost. You all spent. And so the rate at which something changes and its value are not the same number. They can be totally different. And so that's what I'm trying to emphasize here. And this number here is the 30 centimeters per second squared. The reason I would say it is not 0 is what would 0 acceleration and 0 speed mean? Well, 0 acceleration would mean don't change speed, right? It means that you change your speed by 0. So whatever speed you have, a moment later you have that same speed. And that is not what's happening here. Watch. This has 0 speed when I let it go. But a moment later, it doesn't have 0. If I were to put this on the edge right here, that is what 0 speed and 0 acceleration looks like. 0 acceleration says don't change your speed. So if you're 0, a moment later you're 0. And a moment later you're still 0. That's not what I have here. What I have here is when I let it go, I have 0, and a moment later, I don't have 0. There is a change going on. And so as we fill in this chart, I really think maybe the hardest one for the beginning student to really comprehend is that is not 0. It is changing. Again, maybe a silly example, but your life is probably that way right now. You're a student. And you've got a lot more studying to do before you get your degree. And probably a lot of you are engineering or science degrees. And I would say right now, because you're a student, You're a young adult. You probably have zero money. But that's changing. Now, it's going to take a few years before it changes. But in a few years, you'll get your bachelor's degree, and before you know it, you'll be like getting this job making $70,000 a year going, whoa, that was a change. Exactly. And in fact, I would encourage any of you, to do as much schooling as you can, because if you, sacrifice a couple of classes so that you can, have a job, just remember then you've given up a year before you're becoming an engineer, or 2 years. And that might be $70,000. And so I always say, it's probably worth those student loans, because as soon as you get done, boom, all of a sudden you're making $70,000. You go get a job now and you're making minimum wage, what is it, $13 an hour, which isn't bad, and you obviously have to have enough to pay your bills for today. But get out there. Over a lifetime, you'll make a lot more money. Well, that's a little sidetrack there, but hopefully you see that difference between what you actually have and what is changing. And in fact, this makes filling in the table, I think, pretty easy. Because after 1 second, what's the acceleration? Yeah, for those of you who said 30, right? It's the slope of that hill that determines the acceleration. And if you look at that hill, that incline, it has the same slope. So when it gets at 2 seconds, what is the acceleration? Yeah, 30. We call this a constant acceleration. What is it after 3 seconds? 30. What is it at 4 seconds? 30. Of course, then it goes off the end, and so that's a different story. But if I show you again, and I put it over here and I let it go, 1/1000, right here,